we're going to see the relation between the exchange energy and the exchange Hall. So within the constant method, the exchange and correlation energy functional could be composed in two different terms, the exchange energy functional and the correlation energy functional. And the exchange energy functional is defined in this way here. So basically we have the average of the electron-electron potential calculated considering the constant wave function minus the Hartree contribution. So we could calculate that exchange energy function in terms of these constant wave functions. And actually, it's very easy to do, very straightforward, in the sense that we just need to apply or follow the same paths we follow in the case of the Hartree-Fock approximation. Because basically here the constant wave function is Slater determinant. So we are getting basically the same result, but considering the constant wave functions. And if you remember, just calculating this term here, the average of the electron-electron potential, we got two terms. One was the direct term, which basically was the Hartree contribution, which therefore the direct term is cancelled with the Hartree contribution here in order to calculate the exchange, and the other one, which is the remaining one, which is the exchange contribution. And this is the expression that we got actually for the exchange contribution in the Hartree-Fock approximation. And here we have basically the same one, but the wave functions we have here are the constant wave functions, but the expression we have here is basically the same. Alternatively, we could also use the pair density or the reduced pair density in order to calculate this average here. So we could express, therefore, the exchange energy function in terms of the reduced pair density. Okay, just writing this average here in terms of the reduced pair density is just this expression here, where here we have the reduced pair density within the constant approximation. So this is basically the first contribution here. And then we have minus the Hartree energy, which the Hartree energy is just the classical energy somehow for this charge distribution, which is this expression here. Okay, we know that the reduced pair density can be split in these two contributions here. In the first one, we just have the product of the two densities evaluated at R and R prime. And in the second one, we have the product of the density times the reduced exchange Hall within the constant approximation. Okay, just considering that decomposition of the reduced pair density, we can see that the first contribution here it's cancelled with the Hartree energy. So the only one, the remaining one, is this one, which is the one which is related with the exchange and correlation, the reduced exchange and correlation density. But here, as we are considering that the wave function is the constant wave function, Slater determinants, there is, by definition, there is no correlation. Therefore, in this, in principle, exchange and correlation reduced Hall, the only remaining contribution we are considering when the wave function we are considering is the constant wave functions, is the exchange contribution. So there is no contribution associated to the correlation. So therefore here, considering again the constant wave functions, we are just considering the reduced exchange correlation, the reduced exchange Hall here. So therefore, considering that, we could write the exchange energy function in terms of the reduced exchange Hall within the constant approximation. And if we compare both expressions, you can say therefore that the product of the density times the reduced exchange Hall within the constant approximation is just basically this one with the minus sign here. Okay, this one. So therefore here we have an expression for that reduced exchange Hall within the constant approximation in terms of the constant wave functions. But actually, we could also calculate the pair density from the beginning. And actually, it's straightforward because in the sense that it's basically we could use the same strategy that we followed to get the Hartree-Fock energy. And actually, if we're doing that, calculating the pair density within the constant approximation, just using the constant wave function, we are getting two different contributions. One is the direct contribution here, and the other is the exchange contribution. Again, the same way as we got in the Hartree-Fock approximation, but here we are using the constant wave functions. So the direct term here, as you can see, we can write as a product of the two spin densities, and then we have the exchange here. Considering the definition of the pair density, we could write the pair density as a product of the two densities plus the density times the exchange and correlation whole here within the constant approximation. But again, as we are considering here that the wave function is going to be the constant wave function where there is no correlation here, so if we are connecting that definition with the expression we have here, there is just the contribution associated to the exchange. So therefore, here we have an expression for the exchange whole in terms of the constant wave functions. The density times the exchange whole within the constant approximation is given by that expression. And actually, from here, we can easily derive the previously expression for the reduced exchange whole within the constant approximation, which basically is the spin sum of that expression here. Okay, it's interesting to see also that that expression, in this case, the exchange whole within the constant approximation satisfies two very interesting constraints. This is one here, and the other one is this one, which is also very interesting. It can be shown that the exchange whole within the constant approximation is always negative or zero. It's never positive. That's very interesting in the sense that whenever if you need to make an approximation for the exchange whole within the constant approximation, you need to satisfy that constraints here. That's important to have in mind. So therefore here we have seen, as we said at the beginning, the relation between the exchange energy and the exchange whole, which is given by that expression here. And therefore, considering that expression here, we could interpret in principle the exchange energy in the following way. It could be the electrostatic interaction between the electron and the exchange hole. And actually, using the constant wave functions, we could say we have seen that the product of density and the reduced exchange hole within the constant approximation can be written in this way in terms of the constant wave functions. And besides that, we also have that this exchange hole, or the reduced exchange hole within the constant approximation, satisfies these two interesting constraints. Actually, sometimes this exchange energy functional, it's also defined in terms of a neo function. So if we write this exchange energy function in this way, so basically the integral of this function here times the density, so where of course this function here, so considering that that should be the same as this one, should be therefore this one, this function is actually, this function epsilon x is actually the exchange energy per particle. So sometimes this function is also defined, and sometimes the exchange energy functional is also defined in terms of this new functional here, or in terms of the exchange energy per particle. But what's important here is that we have seen the relation between the exchange energy and the exchange hole, and also some constraints associated to that exchange hole.